Welcome back. In this lesson, we're going to be looking at current carrying conductors and magnetic fields and their applications. So let's first start off with just a little quick review. Okay, so if we recall, there are electrons in a wire and it is called current when they move. So example 1 here says to calculate the current and the number of electrons in a wire in which 20 coulombs of charge passes through in 4 seconds. So let's first find my current. If we remember, my current is my movement or my speed of charge. So it's coulombs divided by time, which is the same thing as 20 coulombs in this case divided by in 4 seconds, which will end up giving me 5.0 amps. So now we found my amps. Okay. Next, we're going to find the amount of electrons. So we know the charge of electron is 1.6 times 10 to the negative 19. We know we have this, or coulombs, and we know we have this many coulombs. So we're just going to cancel out our units of coulombs to figure out how many electrons there are. So my electrons is going to equal to 20 coulombs divided by 1.6 times 10 to the negative 19 coulombs. And when we do that, we're going to end up getting 1.25 times 10 to the 20 electrons. But because of my significant digits, I'm going to have to leave that at 1.3 times 10 to the 20 electrons. Okay? So, now let's go into some new stuff here. So to calculate the size of force experienced by a moving charge, like a charge in a wire, it is very, very easy to do actually. So all we have to look at is my force, my magnetic field, my current, which is the speed of the electrons going through, or the speed of my charge, multiplied by my distance, and we're going to go, depending on the angle, sine theta. Now, in this class, most of the times we're using a 90-degree angle. And if we remember from math classes and trig and math, we know that sine 90 is equal to 1. So as soon as we're using a 90-degree angle, we're going to ignore it. And we also know that at a 90-degree angle to the magnetic field, if we look at this picture here, at a 90-degree angle, that's when it's going to cut the fields the best. This electron flow or my charge flow will cut the fields most efficiently at a 90 degree. So right here we have, once again, B for my formula is the magnetic field and it's measured in Teslas. I is my current and it's measured in amps. L stands for my length and it's measured in meters. This is a key thing to look for because most of the time we're going to be seeing them in centimeters or maybe millimeters, but we want to always convert it to meters. And Q is the angle the wire makes with the field. So let's take a look at this here. I have a nice little diagram. So it says here we're going to look at conventional current. When electric current in the wire is viewed in conventional current, that means it is positive. So in this case, we're going to have to use my right hand. So my right hand is going to follow the magnetic field going north, and we know everything's going this way. So it's going to be coming out of the page, or in this case, if we're looking at it, it's going to be going up. Okay, so my current's going this way, my magnetic field goes from north to south, and we're using my right hand because it is conventional current, which is positive, so we're going to use right hand. And we know my force is going to be pushing it up. Okay, so in the second image down here, now I have a negative current going in the opposite direction. So we follow my hand again, current, magnetic fields north to south, so my force is going to be coming up. So we still follow the same rules that we did before. All right, now let's look at my first example. And this one here is just to check our understanding. A wire is 75 centimeters long. It carries a current of 6 amps. The wire is at a right angle to the magnetic field and experiences a force of 0.350 newtons. What is the strength of the magnetic field? So first we're going to start with my formula. We're going to know force is equal to my magnetic field multiplied by my current multiplied by my length of wire. And then since it's already going at 90 degrees, we know sine of 90 is equal to 1. So we can ignore that. Now it says we want to figure out what is the magnetic field, so we're going to isolate for my magnetic field. So I'm going to have my magnetic field is equal to my current multiplied by my length divided by my force. Okay, so I'm going to now substitute everything we know. We have 6 amps, which is my current. We have my length is 0.75 meters. And we have my force, which is 0.35 newtons. I plug that into my calculator, and I'm going to end up getting 12.9 Teslas is my magnetic field. Okay? All right. Let's take a look at my second one. Here's my second example. For this one here, we're going to have to look at it a little bit more intensively. So it says an 8.5 centimeter length of conducting wire lies perpendicular to an external magnetic field of 4.2 Teslas and a charge flow of 2.1 amps as shown above. Calculate the magnitude and the direction of the force of the wire. So we're looking at this part here. Okay, so this is the part in the magnetic field. It's 8.5 centimeters, and we want to know the force and the direction of the wire. So first, let's figure out what will be the force, and then we're going to figure out what the direction is. So once again, we're going to follow up with our exact same formula. We're going to be looking at the formula right here, where we have my force is equal to my current multiplied by my length of wire multiplied by my magnetic field. Okay? So here we know my length of wire is equal to 0.0085 meters. I know my magnetic field is equal to 4.20 Teslas, and I know my amps, or my current, is equal to 2.1 amps. Okay, so let's plug everything in here to find my force. So my force is equal to 2.1 is equal to 2.1 amps multiplied by my length, which is 0.085, and it's multiplied by my Teslas, which is 4.2 Teslas. Okay? Now, I multiply that all together, and I'm going to end up getting a force of 7.5 times 10 to the negative 1 newtons. Now, if I look at this, we have to use my hand rules to figure out which direction this is going in. So we are looking at its electrons, so I have to use my left hand. Okay? My field is going that way. Okay, so we have electrons. My field is going that way, and my thumb is going this way. Okay, so we're going from north to south, and my electron flow is going that way. And we're using my left hand. So in this case, so like that, we're using my left hand. So in this case here, my force is going to be going down. So in this case here, my answer is 7.5 times 10 to the negative 1 newtons, and this is down. And that is going to be my answer. Now let's take a look at my next question. In this case here, I have a 50 centimeter wire with a mass of 5.6 grams, carries a current of 0.25 amps. The wire is at a right angle to a magnetic field and remains suspended in the magnetic field. The strength of the magnetic field is what? So in this case here, we're trying to figure out my magnetic field strength. We know my length of the wire is equal to 0.5 meters. We know my mass, must always be in kilograms, is 0.0056 kilograms. I know my current is equal to 0.250 amps. Okay? Now, we say it's being suspended, so then my force of gravity must be equal to my force of the magnetic field. So magnetic field force must be the same as my force of gravity in order for them to balance out. So I'm going to have here my force of gravity is equal to my force of the magnetic field. We know force of gravity is mass times gravity. We know my magnetic field is current times the length times the magnetic field. Okay? Now, we're trying to solve for the magnetic field, so I'm going to isolate for B. So magnetic field is equal to my my mass times gravity divided by my current times length. All right, so I plug this in. I'm going to end up getting 0.0056 kilograms multiplied by 9.81 meters per second squared. And that's going to be all divided by 0.25 amps. And we're going to multiply that by 0.5 meters. Okay. So now when I calculate that all, I'm going to get my magnetic field is going to be equal to 4.6 times 10 to the negative 3 Teslas. And that is what's keeping it up. So in this diagram, we notice here we have a current conducting wire, or R, and we have a magnetic field, and we have a power supply. So one thing to remember is black is always going to be, it is normally my negative, and my red is normally my positive. So in this case here, the current is going to be flowing this way. So now if we use my hand rules, we know we're going to be using my left hand rule, okay, because we're looking at current. So I'm going to look at my left hand rule, and I'm going to go down into the page, but my current is flowing that way. So I have to turn my hand this way like that, okay? So my force is going to be going into the magnet. If we're looking at that here, my force will be going actually into the magnet, because my going there, so my fingers point down that way, my thumb goes this way, and my force is going to be going into the magnet. So now we're going to look at two current-carrying conductors and how their magnetic fields interact with each other to create forces and what's going to happen. So here we have one current-carrying conductor taking electrons and going down, and on this side we have a current-carrying conductor going in the opposite direction. So to figure out what the forces are going to be, we're going to have to look at their magnetic fields. So let's first look at the magnetic field of this one here. So we're going to have to use our first thumb rule, and we're going to be using our left hand because it's an electron. So it's a negative charge. So I look at my left hand, it's going to be going, if I look at this arrow is coming towards me in the page. So I put my thumb towards me. Then I have my fingers coming down. So on this side of the current carrying wire, my magnetic fields are going down, because that's the way my hands are showing. And then if I wrap my fingers around, it shows my magnetic fields come back up on the other side of the wire. So it looks something like this. Here are my magnetic fields. They're going down. And then here, my magnetic field is coming back up. Okay? Now let's look at my second one. So if I look at my left hand, or my first hand rule for this one here, it's a current carrying wire. We want to find the magnetic field. We know my current is going up the page, so I'm using my thumb. It's going up. Up is out, away from me, and my wire is going, or my magnetic field is coming out of the page on the outside. So on this side here, the wire it's coming out of the page, my magnetic field lines. And if I wrap my fingers around on the other side, so here's my wire, on the other side of the wire, it's going to be going down. So on this side, my magnetic lines are going down and into the page. So I look at the back of my arrows. It's into the page. Now, let's look at this a bit closer and what this means. So in this case, if we're going over top, my current is going, or not my current, my magnetic field lines are going in this direction, because they're if they're going over top, my magnetic field lines are going in this direction like this. They're going up, around, because it's coming towards us, they're going up, around, and that way. So they're all coming that way if we're looking on top. If we're looking at this one on top, it's in the opposite direction. My magnetic field lines are all going that way on top. Okay? And then underneath, they're going the opposite way. They're looping back. So underneath, they're kind of going this way. Now on the top, if we look at this, they're both repelling each other, and underneath they're both repelling each other because my magnetic field lines are going the opposite way. So in this fact here, looking at our first hand rule, we know that our magnetic field lines are repelling each other, therefore my force is pushing them away, so that's what's going to happen when we have current flowing in opposite directions. Now let's look at what happens when current flows in the same direction. So if we look at above, this one's going down. We already know using my hand rule it's going to be going down because once again, current's coming in towards me, and on the inside, my magnetic field lines are going down, and on the outside of the page, my magnetic field lines is going up. So here's my magnetic field lines. We're going into the page here, and we're going out of the page here. This one here's the same thing, coming into the page. So on this side, on the right side of the line, it is going to be into the page and out of the page on the left side. Okay? Now I look at that here. Make one more. Now if I look at that here, what's happening is my current going over top, my magnetic field going over top is going this direction. My magnetic field lines on this one going over top is going like that, okay? Because it's coming up here and then it loops over to this one. Up here, loops over to that one. If I look at these, they're in the same direction. So if they're in the same direction, they're going to continue. These are going to be attracting.